what did with the laser pointer? Okay, let's kick off again, because we want to finish in time for lunch. Where do we all go for lunch? Is there somewhere nice? Okay, I was going to quickly run through how solar cells work, but I think I can now skip this, right? Yeah? Just skip over, good. Alright, so let's think about that. So the big thing, just to recap the last slide, is of course going from bilayer, we're limited by the efficiency because of the exciton diffusion length. So the way around this was to go to this bulk heterojunction. And I've drawn it like this as a simple two-phase mixture of a p-type and an n-type. You'll hear much later, you'll hear during the week that of course it's a much more complicated picture than that. We don't just have a two-phase mixture where we have a p-type and an n-type. We have a much more complicated, we probably have a crystalline P or N phase, an amorphous P or N phase, perhaps a mixed P and N phase, an amorphous N phase, and maybe a crystalline N phase. So it's a very complicated, potentially complicated morphology to probe and understand. It's not at all like these simple diagrams that we draw, but to kind of understand some of the reasoning. And so I don't have to go in and update all my slides, I'll keep to this simple picture. But for example, I know Natalie Stingler, who's talking later in the week, will talk more about this problem. Okay, and if we think about the flavors of these bulk heterojunction devices, basically, if we keep the donor material as a polymer, we can think about 3 different acceptors. I have a fullerene, which turns out to be the best acceptor typically that we've found so far, so it gives the highest efficiency devices. Inorganic acceptors, so zinc oxide perhaps, or polymeric N-type acceptors, and generally the best are here. So the key challenges in this field really are to try and improve the efficiency. So the efficiency of the device, this should say proportional, not equal, is proportional to the open circuit voltage, short circuit current, and the fill factor. And you've already heard a lot about these this morning. But in terms of how we can think about designing new materials, it's good to think about the origin of each of these device properties and how that relates to the materials that we choose to use in the bulk heterojunction device. And the simplest one to understand, at least from a synthetic point of view, is the origin of the VOC. So that's generally determined to be related to the energy offset between the N-type, so the LUMO, sorry, the N-type, and the HOMO of the P-type. So we'd like to increase the voltage of the organic solar cell, so we'd like to go from a typical P3HD PCBM cell to something that's more like silicon. And one way to do that is to make the P-type less electron rich, make it harder to oxidize, so move this HOMO further away from the vacuum level, so increase the ionization potential. That's quite simple to think about how we can do that synthetically. Or conversely, we could take the fullerene and make the LUMO less stable, so push it up towards the vacuum level. And you'll hear more about fullerenes again later in the week, but some of the approaches to this are, for example, to put 2 substituents onto the fullerene ring instead of 1. So to go from PCBM to bis PCBM, you destroy one of the double bonds, so you make it less delocalized, you push the LUMO, you make the band gap wider basically, so you push the LUMO up, that gives you an increase in voltage. The penalty for that in terms of fullerene is that the fullerene then becomes less crystalline when you have 2 substituents on the fullerene ring. You always have a mixture, the geometry of where these 2 substituents are, so that makes the fullerene less crystalline, and sometimes this PCBM doesn't work particularly well with, for example, low band gap polymers, because both the polymer and the PCBM, or the bis PCBM, are relatively non-crystalline. And if you don't have one component of your blend that's crystalline, you don't seem to get good device performance. But anyway, enough of that. I'm not going to talk about N-types, just P-types, because you have other speakers that will focus on N-type. So the simplest way to think about this would just be to make the donor polymer harder to oxidize. And how do we know this? Well, for example, this is a study a few years ago now by the Kanaka group, where they looked at the HOMO position of a range of conjugated polymers, and they could relate that to the measured VOC against PCBM. So there seems to be a definite empirical relationship between the level of the HOMO and the voltage that you observe in the cell, provided, of course, that the anode and the cathode are well matched. An additional advantage of dropping down this HOMO in terms of molecular design is that can improve the intrinsic air stability of your P-type semiconductor, your donor material. If your donor material is too electron rich, it can react with oxygen and or water in the ambient atmosphere and generate undesired carriers, basically, so your dark current will go up. So if your material is too electron rich, that can be a problem. If you make it harder to oxidize, you can increase the voltage and you can also make it intrinsically more stable. So that's one way. Of course, you have to be slightly careful here. If you just decrease the, or make it harder to oxidize, you'll increase your VOC, but your band gap, your optical band gap, will get larger if you don't do anything to the LUMO. If I just left the LUMO where it was here for this donor polymer and theoretically just move the HOMO down in energy so it gets harder to oxidize, your VOC will go up, but I would absorb less sunlight, so my JSC will go down. So there's always a balance between the two factors here in trying to design a new material. We'll talk about how we can think about tuning the energy of this HOMO in a bit more depth over the next few slides, but here's some of the kind of overview. So we can think about, as somebody already asked, twisting the material out of conjugation. So that will make the band gap wider, make the VOC higher. We can think about changing the electron density on the conjugated polymer backbone. So for example, changing from carbon to a more electron deficient heteroatom like nitrogen. So from 5-ene to thiazole. Excuse me, this will make the material harder to oxidize, so you break down. You can change the conjugation length of the material, so you can go from polymers to discrete oligomers. So you decrease the amount of overlap here, and you increase the band gap. Or you can change the aromaticity of the ring system, so you can make it more or less able to delocalize fully along the backbone. So if you go from a material like 5-ene to a fused thieno-5-ene that has a higher aromatic stabilization energy, that has less, well, there's a bigger penalty to pay, but that's going to fully delocalize along the backbone. So you tend to get a wider band gap, and therefore an increased VOC. So as I kind of already mentioned, if we think, so the VOC, we can quite simplistically think where that comes from. The JSC, again, you think about how that relates to molecular properties. That mainly relates to the band gap of the semiconductor. So if we do decrease the HOMO to increase the VOC, we need to make sure that we reduce the LUMO at the same time, or ideally perhaps by an even bigger degree. So we both increase the voltage but reduce the band gap of the donor material and therefore harvest more photons. So we'd like to go from something like this, which is PTHT, to something like crystalline silicon, where we can absorb more of the solar spectrum. So in other words, we have to be careful how we play around with these. It's a balancing act between the band gap and how much current we can get out and the voltage. So there's always kind of a tuning to do there. And the third component that's very, I do have it correct now, proportional, is the fill factor, which is less easy to relate to the molecular properties. That's kind of a measure of how easy it is in broad brush terms to get the charge out of the device. And that really relates, well, it relates to a number of factors, but most controllably perhaps the microstructure of the blend. So you need to be able to both harvest all the excitons, but then when you've split the excitons into charges, you want those charges not to recombine, and you want them to be able to percolate to the respective electrodes. That's kind of much harder to design into a material. How do we think about making materials that are going to give us phase segregation on the kind of 20 to 30 nanometer scale, so that we can harvest all the excitons? The exciton diffusion length is only very small, but also that are going to give us percolating pathways to the respective electrodes. And of course, things that are very difficult to probe, like the molecular orbital, the molecular orientation at the interface between the p-type and the n-type are also quite important with respect to how the exciton splits and whether it will recombine or not. We need some way of stopping that geminate recombination, pulling the charges apart, and that seems to be related to the crystallinity at the interface. If we go from maybe an amorphous type interface to a more crystalline domain, that gives us an energetic driving force to pull these charges away from each other, stop them recombining. Okay, but that's most easily seen, for example, the fill factor. So as I mentioned, it can relate to the morphology of the blend. And you can see this very easily in kind of a blend of PGHT and PCBM, which is really a very well-known and well-investigated blend in this area. So for example, if you take these two materials in a 1-to-1 weight ratio and you cast the film by spin coating, then you get a pretty lousy solar cell. You don't get much current out. If you now heat it up to 140 degrees, then the phase morphology of the blend changes. In this case, the polymer is semi-crystalline, so the polymer seems to crystallize into more ordered domains. You can extract more of your charge and your current goes up. Your voltage doesn't really seem to change in this case, because that's related basically to the energetic offset between the LUMO and the PCBM and the HOMO of the donor polymer. So that's not changing, but by annealing, you're changing the phase behavior, changing the phase segregation, and ultimately changing the performance of the device. So that's quite a frustrating thing in terms of making new materials, because it's quite hard to control what type of phase segregation you get. And really the only tools that we have to do this are kind of trial and error approaches. So we make the blend, we anneal it at different temperatures, see the effect on the performance. We maybe use different solvents or different processing additives that have selective solubility for one of the two components, so that can control the crystallization as you come out of solution. But it's not particularly well understood, and it is a trial and error approach. Let's see. So of course there's always some debate about what would be the ideal structure for these bulk heterojunction devices. People like to draw little cartoons like this, where we have relatively well-ordered domains of, for example, P and N type. We have the P type in contact with the right electrode and the N type in contact with the cathode. So we don't have any shorting. And the domain size here would be twice the exciton diffusion length. So that's very easy to draw on paper. Of course, it's much more difficult to achieve. I don't really want to talk about this in too much depth, because I think, again, some of our other speakers will talk much more about this. But just to summarize some of the approaches, one of the most attractive ones on paper is to take block copolymers of a P and an N-type material. It's well known that you can get block copolymers to phase segregate into a range of geometries depending on the how much each of the blocks likes each other, basically. So this seems to be, on paper at least, an attractive way perhaps to get a structure like this. I think it's fair to say that most of the block copolymers that have been reported so far don't show particularly good performance. And one of the problems, or one of the challenges, is that the chemistry, the synthetic chemistry that goes into making conjugated polymers is not very well controlled. It's not well controlled like it is for living ionization, for example. So it's very hard to get discrete conjugated polymers that have low polydispersity, and then to combine a P and an N block type material into one. It's synthetically a big challenge. It hasn't really been solved. So the performance of block copolymers is disappointing so far. But perhaps there's a lot of potential if we could develop better ways to control the chemistry. Other approaches are, for example, some sort of imprinting here, where you take a polymer that has a solubilizing side chain on it, so you can deposit this from solution. You can imprint it with a stamp. You can then heat it up and do some sort of retro elimination chemistry to turn this from a soluble polymer to an insoluble polymer, and then you can backfill, for example, with a soluble electron acceptor. So this is one way, I think this is from Krebs, where he's trying to define well-ordered domains of P and N type using chemistry like this. So this has maybe got some potential. You can think about taking a soluble polymer and infiltrating it into a well-ordered inorganic N-type acceptor, so titanium dioxide, for example. Well, this is quite a nice approach, doesn't really seem to have been exploited too much, is to take the P and the N-type material and to basically self-organize them into solution, into nano aggregates. So get the polymer to, by adding a non-solvent, to basically collapse upon itself, a theta-type solvent, and then processing these nanoparticles into a film. So again, this was a nice approach, but hasn't really been followed up. One of the problems here is that the N-type polymer that they use is not very effective, doesn't have a very good performance, so ultimately that limits the performance of the device. Okay, but I'm going to talk about how we design main donor materials. And of course, as I mentioned already, we like this roadmap to higher efficiency. So we can make some simple calculations, some simple assumptions based on this voltage versus current band gap dilemma, and think about where we'd like these materials to be. So if you just assume that the acceptor is PCBM, and in this case, in this calculation, which was done in the physics department at Imperial, we've said that the PCBM has a LUMO of 3.7. We've said that we don't need any offset between the LUMO of the donor material here and the LUMO of the PCBM to generate charges. That's maybe slightly controversial, but in this case, this is the assumption we've made. And we've just assumed that the fill factor is 65%, which seems a reasonable number that you can certainly achieve in some organic devices. And if you do that, you can run a very simple calculation that tells you where your HOMO of your donor polymer should be, and it should be somewhere around 5.3 electron volts with a band gap of about 1.6 eV. And if you can hit this sweet spot and get the morphology that you like, then potentially, assuming all these assumptions, you could get a single layer device with an efficiency of around 14%. Okay, so that's kind of what guides us, and you can make different assumptions here. You can obviously change this offset, and this will change the number. So that guides our kind of molecular design. We also need these other factors when we think about the ideal donor material, so high extinction coefficient, so we can use thin films, relatively thin films. That makes it easier to get the charges out. May make it harder to make the device if the film is too thin. So there's again a balance between manufacturability and performance. Many people think a film thickness less than maybe 150 nanometers is too hard to robustly manufacture in a high throughput process. So we may need thicker films. Of course, we need these films to phase segregate, as I've just mentioned. We need the polymer to have relatively good charge carrier mobility, at least equal to the N-type. We need it to be, this is kind of ignored, but we need it to be soluble in printer-friendly solvents. This is actually a reasonably big challenge. Most of the polymers reported so far typically only dissolve in chlorinated solvents, and you can't manufacture, at least in Europe, probably in the US as well, you can't manufacture in chlorinated solvents. They're too toxic, they're too harmful for the environment. So this is a challenge, but we need to use printer-friendly solvents. And that's difficult because we design these materials to have high charge carrier mobility, and that means the aromatics get quite close together. They stack. We're designing them to stack because we need the charge to move from one molecule to another. That intrinsically means they're difficult to dissolve from a kind of fundamental point. So we need to think about ways to process that, maybe learn from the paints industry. And of course they need to be stable. And I kind of mentioned this already. If we just think about an intrinsic semiconducting polymer, if it's too electron rich, the donor material, then in the presence of oxygen and water, you can see that its thermodynamically favourable for the polymer to oxidize. So this would be undesired in the device. Of course, it may be kinetically slow, but it would be thermodynamically allowable. Similarly, for the donor material, if the LUMO is too high in energy, then the radical anion that you form will be highly reactive, so not very stable, and will again, in the presence of water and oxygen, potentially react to give undesired dopants. And there's some quite old literature around where you want these energetic levels to be. Basically, for a P-type material, you'd like the ionization potential to be greater than about 5 electron volts to slow this down. For for an acceptor material, you'd like the electron affinity to be greater than about 4 electron volts, so the LUMO to be lower than about 4 electron volts. For the radical anion to be stable in the presence of oxygen and water. And you can measure that quite simply in a transistor that you take out of the glove box into ambient. And if your LUMO is below about 4 eV, you'll see air-stable electron transport. If it's higher, for example PCBN, the transistor performance dies very quickly. We also have to worry a bit about the photochemistry, especially in the presence of high energy light and oxygen. We can do some irreversible damage to the conjugated polymer backbone. So again, this is quite an old study. Basically, you can excite the polymer to the singlet state, come into system cross to the triplet, excite the state, and then that can sensitize the formation of singlet oxygen in the film, which will then irreversibly degrade your polymer potentially. So you need to protect it either from high energy light or potentially oxygen. So barrier films are quite important in terms of how we think about the future of these types of material. And of course the absolute energy of the LUMO, the polymer LUMO, will affect this. You can see that, for example, in this example. So if you take the very well-known PQHT and you change the heteroatom from 5 to selenium, you don't affect the HOMO energy level, but you can see optically that you reduce the band gap, so you decrease the energy of the LUMO. That means that you have less energy now to sensitize singlet oxygen. So if you just use some very simple degradation measurements, where you take a thin film of PQHT and a thin film of this selenium analog, and you just irradiate it in air and monitor how the absorption maximum decreases over time, you'll see that the selenium analog is actually more stable than the 5 thing, despite the fact that selenium has less aromatic stabilization energy. And that seems to be related to the fact that the selenium analog has a lower lying LUMO, so it's harder to photosynthesize oxygen. So stability starts to become important. Excuse me, oh sorry. It starts to become quite important. Again, this is, I guess, been quite well known in the OLED industry, where people have put a lot of effort into making sure that the emitting polymers or small molecules don't degrade over time, and they're trying to figure out what is going on, what's causing this degradation. So for example, in a blue emitting polymer like polyfluorine, in the presence of UV light and oxygen, you can see that the side chains seem to be reacting with a singular oxygen and then cleaving to generate, for example, carbonyl compounds in the backbone. And that's very easy to see in an emissive material because the wavelength of the emitted light changes as you start to introduce these traps into the backbone. So learning from that, for example, Krebs has just published a kind of a study where he's looked at lots of different donor materials, donor acceptor type polymers, and just looked at the photostability of the thin film as you irradiate it over time, and come up with a sort of general trend. And he's seen that, for example, when you have wide band gaps in conductors that have alkyl side chains appended to the backbone, these materials tend to degrade relatively rapidly. So either for fluorine or cyclopentadithiene, where you have these benzylic type alkyl chains that are easy to oxidize, these degrade quickly. If you get rid of the benzylic, for example, change it from a carbon to a silicon, then you improve the intrinsic photostability. of the polymer. So these are all pure polymers, not blends. So this is kind of a rule of thumb. And this is now, of course, a fairly important area as we get more and more efficient polymers. You need to make sure that they're stable. It's no good having a polymer that's 10% efficient, but it only gives 10% when you first measure the device. If you measure it the next day, it's 5%, even though you may get a nice paper. Okay, so how do we go about controlling these energetic levels in terms of the chemistry? So this is a kind of simplistic overview, hopefully, and then I'll give you some case studies to show how it actually works in practice. So we think about starting something like P3HT, which is thiopene based. If we want to push the HOMO up in energy to make it easier to oxidize, which of course we typically don't want to do, but if we do, we can just append an electron-rich group to the thiopene backbone. So that would typically be something with a lone pair of electrons. Those lone pair of electrons is going to push into this aromatic system, so it's going to overlap with this aromatic system, push its electron density into, for example, an amine or an oxygen, would make the thiopene easier to oxidize. So you know that from P dot. P dot is thiopene with 2 oxygens on. It's very easy to oxidize. It's stable in the oxidized state. It's a conducting polymer. If you want to do what we'd like to do and make it harder to oxidize, then you need to play around with backbone chemistry. So you can change, for example, the carbon to a more electron deficient heteroatom, so nitrogen. If you change from thiopene to thiazole, you make it harder to oxidize. Or you can add substituents to the backbone that are going to pull electron density away from the backbone, make it harder to oxidize. So for example, fluorine. Fluorine is the most electron negative atom, so it's an excellent substituent to make these materials harder to oxidize. Of course, that doesn't happen in isolation. It doesn't just affect the HOMO, it will also affect the LUMO and therefore the band gap. So for example, if you cyanate thiopene, you'll get a slight reduction in the HOMO. It'll be slightly harder to oxidize because of this nitrogen that's now not directly in conjugation with the aromatic, so it's pulling electron density away. It's not donating its lone pair in, but it'll have a bigger effect on the LUMO in this case because of the interaction of the sigma star orbital of the cyano with the LUMO of the thiopene in this case. So it is still an experimental science. You do have to make these materials and measure. You can't always predict. As we've already talked about, quite a nice way of changing the band gap and the conjugation length is to just make discrete oligomers instead of polymers. So you fall back down. So eventually you start to plateau when n is about 20. So the band gap doesn't change. If you go from n is 20 to n is 100, for example, the band gap would change. But if you go from a long high weight polymer where you put in a conjugation breaker, then you can make the band gap wider. So you could make copolymers, for example, of sexy thiopene with a non-conjugated union if you wanted to make a relatively wide band gap material. That's quite hard to do synthetically, so typically another approach is to either introduce a twist into the backbone, that you already spoke about, or introduce what's known as a conjugation blocker. I'll hopefully show you an example. But this is saying the same thing again, basically. So you can control the band gap by changing the number of units that are in conjugation or by making a twist. A conjugation blocker in the backbone will be something that isn't able to fully delocalize from one aromatic across here to the other side. So for example, if you think about a bithiopene unit in the backbone, this would be fully conjugated in terms of how we would describe this chemically. You can push electron density from one aromatic all the way across to the other. If we just follow the movement of electrons, you can see that these two units are fully in conjugation. If you take a cross-conjugated material, you're not able to do that. You're not able to push these electrons around without invoking a 5 bonded carbon, which is not allowed. So if you introduce this material into the polymer backbone, for example, this cross-conjugated material, you'll in effect move back down conjugation length, because these two materials won't be able to talk to each other. So you can see that here, if you compare, so this, where we have the cross-conjugated unit, so here the only units that are now in conjugation are from here all the way to here. If you compare this now to PTHT, where the whole 5-heme backbone's in conjugation, you can see that this effectively pushes you back down this way, so it makes the material harder to oxidize. So this is a UPS measurement of this polymer versus PTHT, which is the one shown here in red. So you can see by introducing this cross-conjugated segment, you've made it approximately 0.4 electron volts harder to oxidize, even though it's an all 5-heme backbone. So that's one way to do it. A second way is to introduce these twists into the backbone. So the easiest way to do this, or one of the easiest ways, is to just control the regiochemistry of these solubilizing side chains that you have on your polymer backbone. You need these side chains, remember, to make sure the material is processable, but they don't just have a passive role. Here you can think about two regiochemistries for this simple 5-heme dimer. And you can have one of the alkyl chains adjacent to the 5-heme, and the hydrogen here, which would be called head to tail, or both alkyl chains adjacent to the 5-hemes. Head to head. If you have head to head, you now get quite a pronounced steric strain between the protons on this alkyl group and the lone pair on the sulfur heteroatom. So you have that twice, both here and here. That forces the material to twist out of conjugation, even in the solid state. In this case, you only have it once, so you have an interaction here between this lone pair and this alkyl, but you don't have an interaction here. So this material, regio-regular PTHT, this would be, which is head to tail PTHT, is able to planarize and crystallize in the solid state. Regio-random PTHT has a much wider band gap because it's not able to crystallize. You have this conjugation, that's where you have this twist in the backbone that makes the polymer both amorphous but also a wider band gap. So one of the problems, or one of the reasons why there's so much or so many studies about PTHT that maybe come to slightly different conclusions, is that the PTHT that people use is not necessarily always the same. So it's often quoted as regio-regular, but the actual percentage of regio-regularity will have an important effect on both the band gap and the energetics. And what's sort of printed on the label is not necessarily true when you buy it. So you should always measure it by NMR, for example. So PTHT is actually a very bad material to use as kind of the fruit fly because of this problem, because of the fact it's not regiosymmetric.
Pardon?
Yep.
So what synthetically can you do to tilt in the favor of head to tail?
So there's basically, it depends on the route that you use to make it. So there's various cross-coupling methodologies that give different, depending on the monomer that you use, will give you different amounts of head to tail, and also how you purify it. So that's quite important. Usually the low molecular weight component tends to have more defects, and that's quite easy, or can be quite easy to remove, but perhaps on a commercial scale it isn't always. So we'll talk about that a bit more tomorrow. But yeah, the chemistry of how you make these is quite important, and that applies to all polymers actually. You can make the same polymer by 3 or 4 different synthetic routes and get a completely different performance depending on the defects. And that's not always, I guess, talked about or appreciated maybe. Okay, so we can have, so usually that's not particularly desirable because that will affect the ability of the polymer to crystallize. So it will affect the band gap, which perhaps you want, but if the polymer is amorphous, you're going to have a very low charge carrier mobility, so that's not good, or not necessarily good. So sometimes you could, for example, two benzenes fused together have an even more pronounced twist than 2 5-hemes because of the orientation of these ortho protons. They're closer together, so that makes 2 biphenylines twist more. So sometimes you don't want that. So you can fuse the two rings together. That forces them to be in conjugation and stops, in this case, the undesirable twist. But you have to be a little careful. It doesn't about what the heteroatom is that you're incorporating. So for example, if you just think about this example where we've looked at, or Matska, I should say, has looked at a trimer and a tetramer of just thiophene, and then if he forces the rings to be coplanar by bridging with a sulfur atom, he doesn't actually make the band gap. You might, from what I've just told you, expect the band gap to get smaller in this case because you force the two molecules to be talking to each other. You force them to conjugate. But in this case, that doesn't happen. And the reason is that if you think about what the sulfur is now doing to the LUMO, if you just do some simple DFT calculations, you can see that this is actually a destabilizing influence because the orbitals are out of phase here between the sulfur and the carbon that's adjacent to it. So it's not always necessarily a simplistic argument that by forcing excuse me, materials to be coplanar, you'll make the band gap smaller. And we also have to watch out for planarizing influences. So for example, you'll recognize this as a head-to-head configuration. And now we've changed from a methylene, so CH2, to an oxygen. So instead, now this becomes, instead of forcing the materials to twist out of conjugation, it actually forces them to planarize. There's an interaction now between the anti-bonding orbital on the sulfur and the lone pair on the oxygen that allows the material to planarize. Also, the van der Waals size of an oxygen is smaller than a methylene and a CH2, so you don't get that steric interaction. So here we do have a head-to-head configuration of the solubilizing groups, but the material is coplanar, and therefore has a low band gap. You can get the same type of interactions between fluorine and sulfur. So this can be one way, for example, to control the reorganization energy of the polymer backbone by introducing halogen-sulfur bonds. It makes the materials really coplanar. Of course, the difficulty is it makes them insoluble, typically, because it makes them very flat and therefore difficult to dissolve. So it's always a kind of a balance between the two. And again, you can see the planarizing effects. You don't have to believe me, you can look into the literature. You can see, for example, if you look at this copolymer reported by Mark Watson and all, so it's a donor acceptor type polymer. With bithiophene, if you go from bithiophene to a head-to-head dialkyl, you do get this twist, so you make the polymer wider band gap. You can see that quite clearly in the absorption maximum or the ionization potential at the level of the HOMO. If you make this alkyl chain even bulkier, so ethyl hexyl, makes the twist even bigger, so it makes it even less delocalized. You're falling back down that the delocalization pathway, so it's harder to oxidize. But if you go from alkyl to alkoxy, now you'll see the band gap actually gets smaller. So it's able to both planarize and you're pushing electron density into the thiophene ring. So you're pushing the donor part, the donor acceptor, up in energy, giving it a lower band gap. How am I doing for time? Probably running a bit late, so maybe I'll skip over that. Okay, yeah, this is basically, so how do we prevent out-of-plane twisting, this undesirable out-of-plane twisting, if you don't think about substituents, but just the actual aromatic units that you're linking together? You can think of this in two ways, and I'll start with this one, which is easier, perhaps. So if you just do some simple models in the gas phase, and you look at the geometry, so this would be the destabilizing interaction between this hydrogen and basically the lone pairs on the sulfur versus, for example, a biphenyl. You can see that the protons here are much closer, so they're within the van der Waals radius of each other, so they don't like to be coplanar in the case of a biphenyl link. You can see that here. So they like to have a twist. Whereas the biphirephene unit is quite easily able to coplanarize, even in the gas state. Or you can think of it as the fact that phirephene is less aromatic than benzene, therefore it has more quinoidal character, so the LUMO is lower in energy, and the quinoidal character corresponds as a double bond character between the two aromatic units. So basically when you go from benzene to phirephene, this linkage has more double bond character. Double bonds have to be planar because of the sp2 hybridization. So this material is happier to be coplanar versus this material because there's a bigger aromatic stabilization energy for benzene versus phirephene. So to go from this to this is a much higher energy to pay than from this to this. So in other words, this material would prefer to sit this way. So there's less double bond character between the two biphenylines, therefore there's a bigger twist. So kind of already mentioned this, of course, the side chain doesn't have a passive role, it can also influence the ability of the polymer to crystallize. So most readily seen for P3HT. If you just change the hexyl from N-hexyl to a branch, you go from a semi-crystalline polymer to one that's essentially amorphous. So it's quite easy, or relatively easy, to change the crystallization of the polymer by changing the side chain. We can also play around with the ability of the polymer to planarize by changing the heteroatom. So we go again, I don't know, can you see this, from sulfur to selenium. I mentioned this before, the selenium is basically less aromatic than phirephene. That means it has more quinoidal character, so it's easier to make. So the LUMO is lower in energy. You can see that from the optical band gap. The HOMO is identical for the two materials, but the LUMO is more stable. The electron affinity is higher. That means that basically the polymer is more coplanar. There's more double bond character between the two selenophenes than there is between the two phirephenes. So the selenophene polymer is able to planarize much more readily in the solid state than the phirethene. Again, you can see that from some simple DFT calculations. You can see that the quinoidal or the LUMO. You can see that here. As you go from the all-phirethene analog to the all-selenophene analog, you don't change the ionization potential, but you do reduce the band gap because you're stabilizing the LUMO. And you can actually see in solution very readily, so these are these four polymers, the all-phirethene polymer versus the all-selenophene polymer. And even at room temperature in solution, you can see that the selenophene polymer is aggregating. So this is the UV spectra of this polymer, and it looks basically identical to the thin film. And that's because even in solution, the polymer's planarized and aggregated because there's more quinoidal character between the two selenophenes. Yeah, or the LUMO is lower in energy, in other words. So this makes the material more coplanar. You can also prove that with some DFT calculations. But I think I'm kind of running out of time, so okay, so another common way that we can control the band gap is to try and stabilize the quinoidal state against stabilize the LUMO. So as you've already seen, the LUMO, the quinoidal state, has the bonds orientated like this. So if you append a unit to the phirethene backbone that can aromatize, so you can see here this pyrazine unit is pseudo-aromatic. In the ground state, this cannot assume the fully aromatic character, but in the excited state it can. In the LUMO, in the quinoidal state it can. So by appending this group, that basically means you make the polymer very low band gap because you're stabilizing this form of the molecule at a gain in resonance stabilization energy here versus here. So one way to tune the band gap, and the prototypical example is this material here. You can see that in the excited state, this can form, oops, my pointer's just run out. You can see it can form the aromatic system. this gives it a very low band gap. Okay, and the last one, the most common approach now is to take, this has proved most popular and highest performing over the last couple of years, is to take so-called donor acceptor systems. So you co-polymerize something that's electron rich, for example this 5-pin unit, with something that's electron poor, this benzophiodiazole unit, and you tend to get hybridization of the molecular orbitals, so the resulting polymer, in this case, will have a low band gap because the HOMO of the polymer tends to reside on this electron-rich component here. So this would be the ionization potential just of this unit. The molecular orbitals of this unit. This would be the molecular orbitals of this unit. And when you co-polymerize them, the polymer takes the characteristics of the HOMO from the electron-rich unit, the LUMO from the electron-poor, and therefore has a resulting low band gap. The only disadvantage of that is if you think about where the molecular orbitals reside, and the HOMO tends to be localized on the electron-rich component, and the LUMO on the electron-poor component, and that can make it difficult sometimes for charges to move, because obviously for electrons to move, for electron transport to move, the electrons are going to move through the LUMO, and then they're going to hop from one molecule to the other. You need those two LUMOs to be in close proximity. Same for the HOMO. So one drawback sometimes with the donor acceptor systems can be low mobility, not always. Okay. I shall probably leave it there. I've overrun drastically because I've still got some slides, but I can move those to tomorrow. So what I'm going to do tomorrow is just take you through, for the first 15-20 minutes, some case examples from the literature, from my own research group, where we kind of put all of these principles together, and you can see how that influences the performance of the donor polymer. Okay? Sorry to overrun. And now I'll take any questions. It just means less synthesis tomorrow, so perhaps you may or may not be happy with that. Any questions? Who's first? Yeah. Okay, so just to repeat the question, the question was, I mentioned that block copolymers don't typically have good performance compared to simple blends at the moment, and what's the problem with that? And I think that, well, there's more than one, is the simple answer. One of the problems is that there aren't many good N-type polymeric materials to replace fullerene, just simply on their own, not even in terms of a dye block. So if you're thinking about a dye block where you are using an N-type polymer, you're always going to be somewhat limited by the fact that performance isn't as good as fullerene. The second problem is that to get good phase segregation in these dye block systems, you need very well-defined, narrow polydispersity blocks that are attached together. And that's quite easy to do in certain types of chemistry, side chain polymers that use, for example, very well-controlled living radical type polymerizations. But in the chemistry that we use for conjugated polymers, we're basically limited to, with one or two exceptions, polycondensation. That tends to give you quite a high polydispersity, so at least 2, maybe even higher. And therefore it's difficult to make very well-controlled dye block materials. If you have high polydispersity, they don't tend to phase segregate very well. So part of the problem is the chemistry, part of the problem is the materials. People have kind of tried to get around that by making a main chain conjugated polymer and linking that to a side chain, perhaps with some fullerene or perylene diamide. But again, that doesn't seem to give, perhaps because you're diluting out the performance of the fullerene, it just doesn't seem to give very good electronic performance. You may get good phase segregation, but you don't tend to get good device performance. But there's still a lot of potential in this approach. I think it is a very attractive approach, but
at the moment the chemistry is not really there for main chain polymers, and the materials aren't really there for N-types.
So I was just wondering if we can tune the LUMO and HOMO separately by adding different functional groups to the benzene ring.
Yeah. Well, it kind of all it's hard to affect just one thing in isolation without the other. What you can do, and has really been, this is I guess the way that OLED has been successful, is instead of making discrete alternating polymers, they tend to take all the bits that they want. So they want something with goods, whole transport, they want something that's emissive, perhaps they want some electron transport, and made random copolymers from all the different components. Because OLED's kind of moved into industrial research now, we don't really know what the best performing polymers are in terms of their discrete structure, but it's excuse me, it seems to be that they quite often copolymerize many different things together to try to control this separately, and that hasn't really been done, or not much, only just starting to be explored really for solar cell polymers, so that's perhaps a kind of good way to go. But the problem there is in reproducibility, getting the same from batch to batch.
So why is it difficult to just bring the technology of OLED to the OPV?
Well, I think there's a few reasons. I mean, I think the first one is probably that the companies that make OLED polymers, there's basically, or OLED materials, is already a market, an existing market, where they can make money. 3 billion a year is not insignificant. OPV is who knows how many years away. So there's obviously less development probably in industry terms, because there's no money to be made really. There's only research materials at the moment. In terms of academic labs, it's quite hard to make polymers that have many components, because typically we only work on a very small scale, and it's much easier actually to get well-controlled and high molecular weight polymers on a larger scale than a smaller scale, because you're limited, as I'll discuss tomorrow, by impurities, and on a small scale impurities can kill you. So it's actually one of the kind of ironies is that if you go to larger scale, you tend to get better performance, but in an academic lab it's quite hard to do things on large scale. So most polymers are only made on small scales. And in fact, it probably even a problem for the field as a whole actually is typically people don't, excuse me, they'll maybe make a polymer, report the performance, but they'll never make it again. So the batch-to-batch variation can be quite large. So if you try to repeat some of the published polymers, you might not necessarily get the same results. And that's definitely a problem. I speak from an industrial background as well. I had several years in industry working in this area. So.
One last quick one in the back.
Okay, you mentioned that annealing temperature can have a dramatic effect on improving the efficiency of the device.
Yeah.
But is the annealing temperature in some way related to, let's say, the boiling point of a solvent? Or is this a maximum temperature, like a peak temperature for a specific solvent, but then can you change that solvent and increase that maximum temperature?
Well, in this case, most examples, the solvent is probably not present anymore, or maybe only in small. So it's actually that you deposit the film from the solvent, and you have your kind of kinetic microstructure that's frozen in, and then you take that film and heat it up to try and get one of the components to crystallize typically, rather than. So I'm not sure that it really relates. I mean, you perhaps could coat the film hot from a hot solvent, and then maybe as it dries and evaporates, you get the microstructure that you want right off the bat without performing a separate annealing step. But of course, it's quite hard to do coating at temperatures, especially around 140. So I don't know if that answers your question.
I think that's probably good. Let's thank Martin one more time.